So I think we're live. Hello, hello. How's everybody doing today? Welcome, welcome. Guten Abend. Let's continue where we left off. So we were looking at Halloween sale. I'm not going to review the problem again because I intend to cut this video into something a little more palatable, a little shorter later today afterwards. Actually, I'll do it immediately after we finish. But this is an interesting problem. And what I'd like to do is continue the math that we were looking at. So I think I could do this in constant time, this problem, and I just wanted to go over how. So, right, we say we've got P, D, M, and S. Then we can define this K to be P minus M over D roof, or ceiling, rather, ceiling of that. And then we can end up with a piecemeal function, piecewise function for the summation, which then we want to consider. We want to find alpha using this piecemeal function. And what we can say is there's three cases to consider: when alpha is equal to less than or equal to k minus 1, or when alpha is equal to k, or when alpha is greater than k. So in these three different scenarios, we have different possibilities. So when alpha is less than or equal to k minus 1, we're looking at this instance. Now the thing to consider though is if alpha is less than or equal to k minus 1, then what we can start with is we know by definition we have this for a relationship between alpha and s given here, right? This is equivalent. And then we say, okay, if alpha is greater than k, then we know by sort of the definition of the problem that this difference has to be greater than or equal to m. That there's got to be at least enough left over after you buy all of the sort of descending portion of the sequence to buy another item. That's if you're greater than k. If we suppose the opposite of this, right? So we have this logical sort of connection. We know that. Then we have the conjunction of that. So if this is not true, then we know that alpha is less than or equal to k. And actually, these are the converse is also true. So if what is it? It's no. Hold on. So, it's the other way around. It's if and only if, I think. That's I think what the key thing to note is that this is by definition, actually by definition of the problem. So if this difference is greater than or equal to m, then alpha's got to be greater than k, and if alpha is greater than k, then this has got to be greater than or equal to m. That is did I get that right? No, it's not. No, this is wrong. It's actually, I did this wrong. There we go. This is what we want. This is what we want. This is, we'll call it a lemma. So, if and only if alpha is greater than k, then we've got this s minus tc of k is greater than or equal to m. Yes, that makes sense. Right. This goes both directions. So, if we know that we removed the whole sort of early portion of the summation, and there's still more to purchase, that implies that alpha is going to be greater than k, right? If alpha is greater than k, the only way to do that is to subtract more, at least 1m, from the difference of s and tc of k. Right. Okay, that makes sense. Got it. So from this fact, we want to try to figure out how to derive alpha. I want to find out what alpha is. Well, scratching my face. You could hear the scratching in the microphone. So this can tell us, so then we can use this check to determine whether or not we're in case 3, right? So we can say if s minus tc of k is greater than or equal to m, then case 3. Oops. Right? If not, or if s minus tc of k is less than m, then case 1 or 2. Right? And then we gotta decide, okay, if we're equal to k or less than k, which this is just less than k, by the way. Okay. Interesting. So if this is less than m, now if s minus t of k equals 0, then alpha equals k. Right? Yeah, if it's equal to 0, then this is just k. If it's less than 0, call it t of k rather than t of c. Then I think we're looking at case 2. Really, this is case 1 or 2, and either way, this is case 1 or 2. Yeah. The tricky part here is like, if it's less than m, but still positive, then that means you're looking at, it's actually the other way around. It's equal to 0. If it's really like this. If s minus t of k is less than m, but greater than or equal to 0, then alpha equals k. Right? And the reason for this is since t of k is less than or equal to s is less than m plus t of k, which this is equal to t of k is the same in this function either side, and this is the second function. Yeah, this is that alpha equals k case. How about alpha is less than k? If so, this is less than 0. Yeah. Now this is if this is less than 0. Then this has got to be case 1. I realize this is kind of long-winded, but I think it works like this. So case 3 is if you have more than one m, right? Certainly end up you have at least one of these. It's case 3, and you can compute alpha from here from this equation, right? Case 2 is you're somewhere between these two, so you don't have quite enough to get another one. But you do have enough to get all of this. That means that alpha is equal to k, which is the second case. And the last case, or the first case, is when you're in this stage and you've got to compute alpha given what do they call that? Given t of c, given s rather, and that is, yeah. So this is going to be s minus t of alpha is greater than 0, which then gives you s minus, looks like alpha plus 1 times p, minus d of alpha plus 1 over 2, and actually looks like this, and this is going to be greater than 0, and we want the largest possible alpha such that this is true. So you end up with s is greater than alpha plus 1 p minus d alpha plus 1 over 2. You can multiply this by 2s greater than 2p alpha plus 2p minus d alpha squared minus d alpha. That gives us 2s minus 2p. Actually, you want to do it the other way around, so we can do 0 greater than 2p alpha plus 2p minus 2s minus d alpha squared minus dA alpha. Which then we can say minus d alpha squared minus d alpha plus 2p alpha plus 2p minus 2s. This is less than 0. Alright, now what we want to do is probably negate this whole thing. Let's get d alpha squared plus d alpha minus 2p alpha minus 2p plus 2s is greater than 0. And then we also want to group terms. Alpha d minus 2p minus 2p plus 2s greater than 0. And we want to now we've got a quadratic formula here. We can simplify a bit. What this is going to look like is, how does this work? It's kind of interesting. So this is kind of an interesting technique we're about to use, but it's the quadratic formula to use to find the roots. So I'll show you what this will look like. So if this was equal to 0, you'd have alpha is equal to negative b plus or minus the square root of b squared minus 4ac, right, all over 2a. So what you end up with is two different possible values for alpha. You get alpha 1, basically if you multiply these two, they'll give you 0. So you can say it's something like this: alpha 1, or just alpha. Alpha, how do you do this? Alpha plus. No. Yeah, okay, so basically you have to move this to the left side for this to be equal to 0, right? So you have alpha plus d minus 2p, yeah, alpha plus this, right, minus this thing, all over 2d, times alpha plus 2 minus 2p plus this whole thing. That's effectively what you end up with. And then you want this to be greater than 0. Now in theory, you just factorized this expression into these two different roots. In truth though, what happens if you multiply this alpha squared, right, you get alpha squared of these two things multiplied by each other. So this would be alpha squared, and it's going to be plus alpha times alpha squared, this times alpha, plus the same thing times alpha. So it's going to be these two, d minus 2p minus this mess over 2d plus d minus 2p plus this whole mess gives you 2d. Yeah, which is what you expect, right? And then finally you have these two multiplied by each other. D minus 2p minus this mess over 2d times d minus 2p plus this mess over 2d. Whew, okay. And that's going to be greater than 0. So that's a sort of off the napkin technique that you can use to find the roots. It's not totally correct. You'll notice something here it's missing, and that's the d. The d is this d here. You probably should have. It actually ends up. It's not that this is equal to this thing over here, if you divide by d, on this expression by d, then it's equal to this thing, which I'm not sure matters all that much. I'm not really sure. But yeah, so you end up with these two different sort of expressions for alpha, and you want to say this times this is greater than 0, which is basically both of these have to be positive. Alpha has to be positive in both cases. Yeah, both of these need to be greater than 0. This and this needs to be positive. Now, how can we check that these two expressions are, in order for this to be greater than 0? Neither, if they're both negative or both positive. So we have so we got alpha plus this thing, d minus 2p minus this, call it q, minus square root of q over, over 2d. It's greater than 0, and alpha plus d minus 2p plus the square root of q over 2d is greater than 0. Let's take this, resize this to 200. And or both of these are less than 0. Okay. Right. Okay. That's what we're looking at here. That's what we're dealing with. So either both of these expressions are greater than 0 or both of these expressions are less than 0. Now, how do we what does that mean for alpha? This piece implies what about alpha? Alpha plus d minus 2p minus square root of q over 2d greater than 0 implies that alpha is greater than, square root of q, right, add the q over there, subtract, you get subtract d minus 2p, which is plus 2p minus d over 2d, assuming q is greater than 0, which is, this is positive, this value, no matter what, and then this I think is also positive, or generally positive. S is necessarily larger than P. Yeah. Well, this is a positive value, this is negative. It's not imaginary, I guess. If we suppose that S is greater than P, because this could just be 0, this alpha. If it's not 0, right? It's actually not possible to be greater than 0. If that's kind of interesting. Math always kind of blows my mind. So like, if it's actually not possible for this expression to be non-zero, you end up with an imaginary number here in this portion, which is kind of cool. But I think that's exactly when S is less than P, then alpha simply cannot be greater than 0. And so this expression gives you an imaginary number for alpha. Kind of cool. kind of neat. So let's just say s greater than or equal to p implies q exists, whereas q is greater than 0. Probably the case. But yeah, you want alpha's got to be greater than this, so alpha's got to be, and it's got to be the smallest value that's greater than or equal to. So alpha is going to be the roof of the square root of q plus 2p minus d over 2d. The ceiling, rather, of that expression. And that, I think, would imply that this other expression is greater than 0 as well. Yeah, because this other expression is necessarily larger. Larger than, right. If this is 1, then this, and this is 2, then 2 is always going to be larger than 1, given that q is non-zero. Q is positive, and then square root of q is positive, which gives you this is already larger. So as soon as this is positive too. So you know you're positive. And then you have a similar thing here in the other direction when you're looking at both negative things. Basically, you're saying that you would say this has got to be negative. Well, that's kind of interesting. Like, is this the smallest alpha? You could say if this is negative, to guarantee that this is negative, you just kind of negate everything here. Or alpha is the roof of, I think it's just the negation of this. Which is less than 0, which we exclude. Is this a word, disclude? Oh yeah. Social exclusion. Okay. Which I think we exclude because, right, if we negate the second piece, then it's the same algebra we just did, except, well, actually, let's see what happens if we do this. Consider this case. This would look like, oh no, this is not possible. D minus 2p, well, okay, no, let's see, so alpha would have to be less than the negation of this, and the negation of that, over 2d. This looks like it's probably going to be a negative number. D minus 2p. P minus d. And p is necessarily greater than d, I think is also. Yeah. Yeah. Well, no, I had this wrong over here. It's actually 2p minus d, it's just negative q here. It would be the floor of this. We want the largest alpha that satisfies this. Well, we need to have, it needs to be smaller than this value. 2p minus d. This is, what does this mean? What does this look like? This is, basically we have negative alphas to consider. Yeah, it's just like if you're using negative numbers. Because this creates a kind of, like a, what's that called? This creates a kind of quadratic function. And there's another way to take a look at this function here. Excuse me. Another way to look at this function is to maximize s minus this function and maximize it maximize with respect to alpha. You can use some calculus. You don't need calculus to do this. And alpha's also got to be an integer. If the thing is, there's a reason why you toss out the other possible values for alpha. No, you're not maximizing this with respect, I'm sorry, you can't do this calculus. You're not maximizing this with respect to, you're trying to maximize alpha, actually. Which means, right, you're trying to solve for alpha in terms of s. That's really what you're looking to do. Excuse me. Oh, this is so confusing. I've done this so many times before in the past, but every time it trips me up when you're using something like a quadratic function in this kind of situation. Basically, you're trying to find the inverse of a quadratic function, which actually is two functions. That's the difficulty. What you get is you don't just want s to be positive. You don't just want this function to be positive, right? You want to find the largest possible alpha such that s is positive. So in other words, you're trying to minimize this function. That's maybe a better way to formulate this, sort of to understand it. Then you can use calculus. You're actually trying to minimize this function, this difference, with respect to alpha. You can you could I think I did I don't know actually. Let me undo all this. This seems kind of wrong. Something about this seems wrong. I like using calculus for this. It's a lot easier to think about. So let's say minimize s minus alpha plus 1 of p d alpha alpha plus 1 to where alpha is positive integer. And then we can say df d alpha is then, right, d alpha of, this is a lot easier to think about, s minus alpha p plus p minus d alpha squared over 2 minus d alpha over 2, which then gives us p and minus d alpha minus d over 2, right? Decuckers, and then we want to say p minus d alpha minus d over 2 equals 0 implies negative, or rather p d alpha plus d over 2, which then gives us p minus d over 2 d alpha, so I guess this alpha equals p over d minus a half. Wow. So the minimum, it's going to be at p over d minus a half, because we know that this is a quadratic formula, which means it's going to look like this. So the way we could prove that, by the way, is we can take d squared of f d alpha squared, take the next derivative of this, and we get which is d alpha of p minus d alpha minus d over 2, which is going to give us negative d, which implies that d squared f d alpha squared is less than 0 at all points. So if we know the second derivative is negative at all points, that means that the slope is always decreasing, which means that we have this kind of a shape. Slope is always decreasing. Decreasing, decreasing, decreasing. Oh, wait a minute. That doesn't seem right. Oh, that is not right. That's why. Okay, I did it wrong. It's s minus this function, which means it's minus alpha p. Oh, I did it wrong. Yeah, it's one of the problems with like doing multiple steps at the same time. So this alpha p is negated, and then this p over here is also negated. And then this negation becomes positive, so this is actually both positive. It's a good thing we went through the whole thing. That's why it's not useful to prove things, you know. So then this becomes S goes away, P goes away, you get negative alpha P, or negative P, plus D alpha plus D over 2. There we go. And then now this is negated. This gives us negative P plus D alpha plus D over 2 equals 0. Which then gives you this other stuff. Which is alpha equals, or rather, D over 2 minus P equals, actually let's do the other way, D alpha plus D over 2 equals P, alpha equals P minus D over 2 over D, which is P over D minus a half. There we go. And now we can take, we get positive D. If we say negative P plus D alpha plus D over 2. If we take this derivative, we get D, where negative P and D over 2 are go to 0, and we take this D alpha of D alpha. I realize having D in here makes things kind of confusing using Leibniz notation. And now we can show this is positive at all points, because it's a constant positive at all points, which gives us this shape. Neat. I feel like I'm these are like mental math muscles I haven't used since I was in high school 10 years ago. It's the kind of stuff I was doing 10 years ago. It's crazy. Still useful. It's awesome. But anyway, yeah. So what that means is we can find the minimum of this function by just plugging in this this alpha P over D minus a half, which is so F of, or let's let Q equal P over D minus a half. And F of Q looks like this. This will actually give you the difference, but no. That's what alpha is. We just need alpha. We don't even care what the difference will be. We just want to know that we want to minimize that difference. So, okay, that's it. P over D minus a half. Now, there's a thing here though. There's a small caveat. Do we take the floor, the ceiling, or the floor of P over D minus a half? Right? Yeah. And we don't know if see, that's a tricky thing. Could be the ceiling, could be the floor. You want to take the minimum of so we say if f of ceiling of alpha, we'll call this alpha prime, we'll say let alpha prime be P over D minus a half if f of the ceiling of alpha prime is greater than f of the floor of alpha prime, let alpha be want the smaller of these two. Yeah. Floor of alpha prime. Otherwise, the roof of alpha prime. So there is a little bit of stuff there's a little extra check you gotta do. But basically this is what it comes down to. So this is case 2. If you're in case 1 or case 2, then you're going to calculate this guy, P over D minus a half, and then compare this function one to the other, which is this guy's S minus this expression. All right, and you pick which one is better. If that's so that's if you're sort of on the you haven't gotten to the trailing part at the end. If you're on the trailing part though, then you're going to perform a different calculation, which is just going to be this guy. In case 3, come on, consider S minus T of K. Right. And let alpha be K plus, and this is going to be as many M's as we can get, so it's going to be S minus T of K divided by M, and you're going to want the floor of that. So and then so this is going to be S minus T of K is what's left over, and then you divide by M to get the number of. Now you take the floor of this, because if there's some left over, you don't want to include it, right? Leftover is just leftover. You can't buy beyond that. So there you go. There's the two cases. So if you're in the first case, which is you calculate this value and determine whether or not it's greater than M or greater than or equal to M. If you're in that case, then you're going to go ahead and say, okay, take this to be alpha, right? And then if you're in the other case, though, then you're going to perform this calculation where alpha prime is this thing, and then you either take the ceiling, you can take the ceiling of alpha prime and the floor of alpha prime, and then you say, okay, compute this function given those two different values, and depending on which one is larger or which one is smaller, that's the key that we want to use. So I think I can do this in a functional way. This is kind of an interesting. This is basically a sorting algorithm with a special key, right? That's kind of what we're doing here. We're sorting these two values based off of what map those values to something else using F, and then compare the map values, and then use the keys, sort the keys based on that map value. It's kind of a neat thing, but it's basically sorting using a special key, where we want to get the minimum value of these keys, and this key is this minimizing function, this function that we're going to try to minimize, or we're going to look to minimize. And then what you want also is that's in the case that you aren't going to have these extra trailing pieces at the end of the sequence, whereas in this case you know you've got the whole section of stuff that you can buy, and then you know you've got this sort of trailing bit at the end, which is kind of trivial to append. And so that seems to be the solution, sort of in its ugly, in all of its gore. Pretty interesting. Neat little exercise here. Yeah, I mean, I kind of knew that, what this was going to look like. But yes, definitely you can do this in pretty quickly, constant time, closed form solution. Almost completely closed form. Not quite, but definitely constant time. But I don't know if you'd call it closed form. It's pretty straightforward, I think, overall. But yes, let's code this up. This would be interesting to do in Clojure. So we'll say first things first. Parsing integers. PDMS answer. And finally, we want to get the total number of games we can get. All right, so let's do this. So we've got S minus T alpha greater than 0. So we've got a few calculations. So first we want to get K, which is P minus M, ceiling of P minus M over D. So say let K be P minus M over D. P minus M divided by D, and then we want to get the roof of that, ceiling, and then convert that to an integer, because it does not return an integer. Okay, and then we want the next thing, which is T of K, S minus T of K. So call that difference. So else we could do this. K, which is S minus T of K is, you can also define this function. What does this look like? This is, call this F. Alright, call F, it's a function which takes alpha and the P is going to be, yeah, it's fine, P and D are just kind of present. So this is going to be alpha increment alpha multiplied by P subtract D times alpha times increment alpha divided by 2. So D alpha increment alpha, right, divided by 2. And then subtract 1 from the other. So that's F. And then we'll say F prime is going to be function of S and alpha, or just say alpha as well. And this is going to be F of alpha, and it's going to be S minus this alpha. We're going to use this later as a key for a sort comparator. And then we want to say call this alpha prime, which is P over D minus a half, or alternatively it's 2P minus 1 over, how do we do this? We could say yeah, so 2P over D minus D over 2D. 2P over 2D minus D over 2D, which gives us 2P minus D. Got it. 2P minus D divided by 2D. Call that alpha prime. So 2P minus 2P minus D over 2D. There we go. Okay, and what we want to do is say if case 1, if S minus T of K, right, so this is diff K, which is S minus T of K, which is really F prime of K, just diff K. I don't really know what to call this, but it's going to be F prime of K. So this function F prime of K, this value, is diff K. If that is less than 0, then we're going to be in case 1. If it's greater than or equal to 0, then we're in the third case. Yeah. It's not just greater than or equal to 0. I think it's greater than or equal to m. So if so now we'll go here. Say if diff K is greater than or equal to m, then we're going to go ahead and return K plus diff K divided by m floor. So diff K divided by m floor, math floor, convert that to an integer, and add K to that, plus K. Otherwise, we got these values, these other things going on, and it's going to be this kind of sorting that we're going to do, which, how do we provide a custom comparator in to a sort function in Clojure? Let's see if we have that sort of built in already. Let's just try Clojure sort. Comparator collection. Compare last one, last two. Excuse me, did not do this. Use sort by instead. Sort by last. There we go. Okay. So we're going to sort by. Oops. place here. We're going to say sort by of this collection. It's going to be, or we can even do this. Map int to math floor of alpha prime and math dot ceiling of alpha prime. So we can map this to get a sequence, right? Or we get this vector, then we can map integer to get this sequence, and then we can sort these by this function f prime. And what we want is, what does the sort by do? 1, 2, 3. So the key, the value at the end of the key is going to be ascending, which means this will actually sort. The smaller one will be first, yeah, which is what we want. So we can just take first of that and return it. Which is kind of neat. And that ought to do that. Should solve the problem. Actually, that should just be it. After that, I think we're done. Let's see what we get here. Let's see how we do. If it compiles even. Pretty unlikely to compile. Java math floor. Yeah. Okay. Really? How do I get the floor function in? Maybe it's just math.floor. I don't know. I don't think so. I'm a little uncertain here. Okay. Why? What's the problem? What exactly is the issue? I thought stop scratching my head. Just gotta stop doing that. Numeric tower. Really? Doesn't have the Java? Doesn't Java have? Do I need to use really? There's a ceiling function. There's a floor function. What do you mean we don't have floor? Need to convert to a double? What? Come on, man. That's depressing. Doesn't work. I don't know, man. Excuse me. Oh, come on, man. It's right there. What do you mean you can't find it? What do you mean? It's right there. What are you talking about? What do you mean? What do you mean? Woo! Alright, leave ceiling in there, but remove floor. And it's just gonna be test, test. Integer function 13. Where is that happening? Here. What's wrong? Huh? I can do this, right? I'm not too sure how I feel about Clojure after all. This gives me a headache. Some of these compiler problems, issues, they're not really very descriptive. Trying to cast an integer to a function. When is that where? Where is that happening? Evoke, main, apply to var, apply to evoke. It's just apply somewhere in here. There's not very many things going on here. Oh, that's my mistake. No, I understand. I was wondering about this before, like if. Yeah, no, that's my mistake. I understand. Let's see what's going on. Yeah, because this doesn't generate a function. Let did not conform to spec. Come on, man. What do you mean? What do you mean? Ah! Excuse me. Testing. Testing, testing, 1, 2, 3. String cannot be closed, cast to a function. This is a function? This isn't a function. What the heck is going on? Holy guacamole, man. My brain. My brain. My brain. Man. Don't even know why it's not compiling. Apply to invoke static eval load eval. String cannot be cast to function. Where is that even happening? Why are you doing that? Why do you think that's... Why does that matter? What? Is that string in here? Maybe this is why this is supposed to be division. Does that work? Where is the problem? I don't even know. It's not clear at all. Just return alpha. What the heck? I don't know. Can we just comment all this stuff out? Where can it even be? Why is the problem? I see what's wrong. You can't just put whatever you want here. This is kind of like, I've run into this problem numerous times where I'm trying to compare these two, and that's why it's giving me a hard time. It's nothing to do with the other stuff. Oh my goodness, this is driving me crazy. It's all just syntax errors. Where is this happening? What is going on? What? What? What is even going on, man? Can we just return test, maybe? Can we just do that? Something that works? Just anything that works? Okay, wrong answer. Good. Great. Fantastic. Get this if in here. We just do if true. Right? How about that? Okay. Let's see. Oh, I know why. Oh my goodness. Holy smokes. Yeah, it's going to take me a while to really get used to Clojure. These are like the kind of pains you got to go through to really understand what you're doing. Because you got to get used to the Lisp syntax. Go through enough pain, you'll remember it. Start to memorize it. So that was wise, because this has got to be everything's got to be a function. Every operator, everything's a function. And this f prime of k, it doesn't work like that. It's f prime the function, and you pass k to it. Let's see. Cannot resolve f prime now. And this was done incorrectly as well. So it's the Lisp-like syntax that's really throwing me off. And then f isn't defined. It should give me that error now too. Yeah. All right. Let's define f. Bring it back here. Okay. Cannot find k. Okay. Excuse me. Okay. Great. So we're able to find ceiling. Now the question is, if we get alpha prime, are we okay? Now can we find floor? Moment of truth here. Moment of truth here. Oh, we found floor. Hey, there we go. Okay, good, great. Holy guacamole. Alright, so that was syntax errors, simple syntax errors, which are kind of hard to pick apart later. Well, hard to pick apart because, oh, come on. Oh, that's why. Yeah, actually it's more of the same syntax errors because this is, that's why I couldn't find the symbol. This is supposed to be a function. And I'm not indicating to the compiler that this is indeed a function. That's why it's telling me I can't find it. Oh, it's so confusing. Yeah, unfamiliarity with Lisp-like is seems to be the problem that we keep running into. Okay, that's wrong. Why is it wrong? What? What? Nice. Oh, okay. Alright. I think this is supposed to be a first, but what happened? I'll do this by hand to debug it. So I don't think I'll be able to figure out what went wrong without. So 23,685. So 23,685 would be 23,685 PDMNS. What's P? P is the starting price. So we would go 85 minus 20, 65 minus 17, 50, 48 minus 14. That's 1, 2, 3. 34 minus 11. 23 minus, where's the boundary? 6, so 8, 4, 5. 23 minus 8, we get 15 minus 6 now. 9 minus 6. That's 3, so this is the 7th one. So this is a case where you have 2 of these things. Yes, 2 extra minus 6s. And so you actually end up in this instance, this case. This should be the easier case. So K, which is, let's just print K. All right, if we run this again. 5. Okay, is 5 in this instance? It is, yeah. So we should add 2 to 5. All right, so we expect this difference of k divided by m. It's not, it is m, yeah, m is 6. So this is 5 divided by 6 could give us 2. 2 something. Shouldn't this be Difference of k is, oh, that's why. It's f prime that I'm looking for, not difference k. Duh. Yeah. Well, f prime of k, in fact. I think that's what we're looking for. I thought it was difference k. Oh no, it's the same thing. Wait a minute, what? That is diff k. What is going on? Huh? Shouldn't this give us 15 in this instance? Super confused. 10. Oh, excuse me. Excuse me. Excuse me. Well, there's a problem. How do we get 10? What? 75. This should be 60, not 75. Or it should be 65. No, excuse me. 70, not 75. How do we get 75? What in the Sam Hill? Diff k is f prime of k. Prime of k is s minus f of alpha. S in this instance is 85. F alpha is, it's going to be f of k. F of k ought to be, in this case, we expect 70 rather. F of k is 70. When we run this, we check this. F of k being 70, what do we get? F of k is 70, what do we get? F of k is 70, what do we get? What does this mean? What are we doing here? What's k again here? That's the key. K is P minus M ceiling D. P minus M ceiling D. That's K. And P minus M divided by D ceiling, which is 14 over 3. This should be 5, which we got. We did get 5. So f of 5 is then, this is f of alpha, I think it's called, right? F of 5 is going to be alpha plus 1 p minus d alpha plus 1 over 2 and take this difference. So in this case, it's 5 plus 1 times p, which is 20, minus d, which is 3, times alpha, which is 5, times 6 over 2, which gives you 20 times 6 minus 15 by 3, which is 80, minus 45. Sorry, 120. Yeah, 120 minus 45. Which ought to give us which gives us 75. Uh-oh. That's not correct. What? 20 plus 17 plus 14. Excuse me. Why am I off by 5? What the heck? 37, 25, 57, 62 plus 8, 70. How did I get this extra 5 here? Oh, maybe this is supposed to be alpha plus 1, alpha plus 2. Maybe that's why. But that throws everything off for me. That can't be right. What is going on? No, this is correct. This is right. I don't know where this extra 5. It seems like this is off by 1. It seems to be the problem. That this is actually supposed to be. What? I'm so confused. Where did I miscalculate? Calculate. I missed something. 20 minus 0 plus 17 minus 3 plus, or 20 minus 3. 20 minus 2 times 3. Oh, I think I see what the problem is. 0, 1, 2, 3, 4. 17, 14, 11, 8. It's 4 times 3. Right. This is the problem. So we range, so the number, so this is 1, 2, 3, 4, 5, right? So we have 5 times 20, not 6 times 20. Right, so this should be alpha times p. And this ranges from 0 to -3, -6, -9, -12, which is minus 3 times actually alpha minus 1, which is 4 times 5 over 2. Right? It's actually the sum. It's actually the sum I equals 0 to n minus 1 of I, which is n minus 1 over 2. That's why. It doesn't actually go to n. It goes to 1 less than n. It doesn't go all the way to alpha. It goes to 1 less than alpha. So you get d alpha minus 1 over 2. Okay. Wow. All right. That just kind of rocked my world because all my calculations are wrong after that. The idea is the same, but this function that we started with has got to be different now. We got to reapply all this stuff. So first things first. This is k. We said is p minus m over d. Floor or roof is. I think this is still the same. Where does this come from now? P minus m over d is. Yeah, that's fine. That's the same. That's the same. Right. If we go back to where we got k from, that doesn't change. See, it comes from this. Okay, so p minus m over d, and then we have the next piece, which is this function. We computed alpha prime. This part we got to use. This part we've got to use. Well, we can just do it this way. Just do it over again. So s minus alpha p minus d alpha minus 1 over 2, right? You look at this, and then you say that's f of alpha. So f prime is going to be, you know, this minus p plus, let's say d alpha of d alpha squared over 2 minus d alpha over 2, right? So as s disappears, it negates this alpha p becomes just negative p, and then this other portion is still positive, which is, this is very confusing, these d's, but is what it is. We'll leave it. We'll just leave it. I can do something about that, but we'll leave it. D over 2. And then now you want to say this is equal to 0. You know, it's a parabola. We can say this is when alpha is, we have d alpha equals d over 2 plus p. Alpha equals p over d plus a half. Which is actually, right, so we divide by d on both sides, get a half, get p over d. We get 2p over 2d plus d. Aha! This also might have been why my calculations before were like so off, or just seemed so off, so all over the place. Because this is clearly positive. It's obviously a positive number. Whereas the other number, it was like not so clear depending on what p and d is or was or are. And now you can say this function here, let this be same thing. This doesn't change either. So the mechanics of all this is the same. It's just this changes to a plus. Sweet. Let's take a look. Oops. No. From subtracting d, 2p minus d, you're going to add d. 2p plus d over 2d. All right. How do we do now? How do we do now? How you like me now? How you like me now? See what happens. I think we got it right now. Let's find out. Oh! Oh! Not quite. Not quite. Oh! Ho-ho! No, sir. No, sir. Oh, well, I gotta change this, that's why. F has gotta change too. I didn't change that yet. That's probably the reason. Yeah, you just subtracted 1 from alpha, that's all. Instead of incrementing alpha here. Leave it where it is. Yeah. It's actually gonna be decrement alpha now. Kind of prefer to put it to the left if I can. Okay, let's see. Hey, there we go. Huzzah. Okay. Submit that. See how it goes. See how we do here. Oh no! Oh, got things wrong after all that. Oof. Oof. Wow, I got 5 of them wrong. Holy smokes. What happened? 0. What do we get? We run this. 101, 199. Well, we could just run these test cases, I guess. Well, I probably missed something kind of obvious. It looks like it's like off by 1 error. Oh, these are 0 or 1 answers. Well, something not particularly good. I don't know what it is. I don't know what I did here. Did something wrong. Hey, Will. Hey, how's it going, Prince Polka? Welcome back. Hello, hello. How are you? Welcome, welcome. How are you? How are things? Hello. Hello. $100? What? Expected was not 100. Oh, okay. What is this? This is 101,199 is... Let's try this again. How did I mess this up? After all that. How? Seems so simple. $101,199. All right. So we have, oh, I see, because P's got to be, we can't afford P at all. S is less than P here. Oh. Oh. Right. I think we assuming that we can actually afford anything, which we can't in this case, and can't in this case, can't in so these 3 cases kind of go out the window immediately. But what about this one, where we can only afford 1 or afford a few? I think these we can only afford 1. Here we can afford 1, I think, certainly. And then here, what are we supposed to get here? For starters, what do we get? Been working today and then hanging out on Discord. Hey, nice. Very good. 6 I got. What were we supposed to get with this? Doesn't tell me what the output would be. I can do it by hand to find out. 119 1. 119 1 180. 119 1 180. This should be 180 minus 100, then which is 80, and then 80 minus 100 minus 19 is 81, I think. So this should just be a 1. Huh? 100 minus 19 to give us 81, which we can't afford. So that's it. So why where did my math go wrong here? I got 6 instead of 1. How come? Something's not making any sense here. I think this is wrong, this idea. It's P over D plus a half. I think this is incorrect. I think this just gives you K again. Something like that. Super confused. One more time. Let's try this. So this function, S minus this alpha P minus... So the thing is, S is a constant. This F prime, that gives us the minimum. But this doesn't make a lot of sense, does it? Because the S could just be negative the whole way. Yeah, this doesn't make a lot of sense. What we really want is, yeah, this doesn't, I don't think we do it this way. I think this is wrong, this idea. I think this is the wrong idea. Because what we want is F alpha to be greater than 0. And minimize F of alpha, right? So we can minimize this. Yeah, I think that's the problem, is that this can be minimized, this function. So it's basically like a parabola like this. It's really, what is it? It's like, excuse me. This decrease, this gets smaller. So this is like one of these. And then we take S minus that, so it looks like this. Which is actually, yeah. It's actually one of these kind of functions. Do we want the minimum of that? That's really confusing. I think so. But that's negative. It could be negative. That's the problem, right? Like this minimum could be a negative value for what we end up here, and this has to be positive only. So actually what we're looking for is when it's 0, and we're looking above and below. One integer above, one integer below, which is a little confusing, but that's actually what we should be looking for, is when f alpha equals 0, not yeah. Okay. It's confusing, but I think I understand. So, all right, we'll go back to our quadratic formula then. So this is S minus alpha P plus D alpha minus 1 over 2 equals 0. This gives us D alpha squared over 2 minus D alpha over 2 minus alpha P plus S equals 0. And now what we want to say is you can multiply through by 2 and divide by D as well. And you get alpha squared minus alpha minus, we said, 2 alpha P over D plus, so multiply by 2 and divide by D. I think just multiplying by 2 is better. Leave everything else where it is, so D alpha squared minus D alpha minus 2 alpha P plus 2S. There we go. Okay. And I'll say you're probably, what is it? I don't mean to be rude. I didn't really like say hi, say how things are, how are things, and what's new, and have you done any interesting problems lately, and any of that. Forgive me for that. I'm kind of like a little too focused at the moment. Although, do I normally do all that anyway? Maybe I don't want to make sound like a liar here. I feel like I don't typically do that kind of stuff anyway. Now this would be incorrect. Yeah, I was just thinking that when I pull out the alpha here, this you actually have to put this negation in there correctly. All right, now we can say alpha is equal to negative b, 2, d plus 2p. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now this 8sd, it is possible that this is imaginary. Is it possible? Yes. Yeah, this could be never 0. How would this be never 0? How could that happen? What would that look like? This function is never 0. That would be like, if this function is never 0, what would that look like? What would that be like? It would mean the lowest point isn't 0. It's greater than 0, which its lowest point is f of this guy. So if you take 2p plus d over 2d and plug that in here for alpha, and then you would show that's greater than or equal to 0. What does that imply? I'm kind of curious what that does, what that means. Sorry? No, no, it's okay. I don't, no, it's okay. I don't, no, it's fine. It's a beautiful day out today, by the way. Not going outside today. We got work to do, but it is beautiful though. It's a very nice day out. Okay, I'm looking for something important here. Here it is. Let alpha equal 2p plus d over 2d. 2p plus d over 2d. Then you get d of 2p plus d over 2d squared minus alpha, which is 2p plus d over 2d times d plus 2p plus 2s is greater than or equal to 0. What does that mean? What does that give us? So you get 2p plus d squared times 1 over 4d, right? It's 4d squared with a d removed, minus 2p plus d squared times, this looks like 1 over 2d plus 2s greater than or equal to 0. Which actually these combine kind of nicely. This is 2 over 4d, right? Which then gives us negative 2p plus d squared over 4d plus 2s is greater than or equal to 0. Which means that 2s is greater than or equal to 2p plus d over 2d, squared over 4d. Which means that s is greater than or equal to this. Which doesn't really tell you too much about anything really. S and P and D. It says we'll have non-zero solutions in the case that, I guess S is very large. It'll never actually hit 0, this function. Okay. Does that matter? Do I care? Why does that? Well, I guess it kind of does, because if we're going to calculate when this function hits 0, well then we minimize. Then we just want to minimize. This function, which is to say to get the maximum value for this, which is exactly k. That's kind of interesting. Basically, you're in the second case if you do this. If you have if S is way larger than P and D, and you're looking at the case where you're going to want to consider P minus M over D, roof ceiling of P minus M over D. Otherwise, you're going to want to. Otherwise, you're correct to use the this guy. No, what's that? Otherwise, you can use the quadratic formula to figure out when this thing is 0, and then you can go the less than, larger than, right? The two values below and above. One of those two values is greater than 0, and that's what you're going to want. For alpha. Obviously, you can't use this quadratic formula in the case that oh no, I'm sorry, I'm wrong. Wait a minute, what am I doing wrong here? Yeah. Obviously, you can't use the quadratic formula in this case because this, by the way, if you look at this, is exactly when the quadratic formula portion is less than or equal to 0, or less than 0 is when this is the case. Or no, not greater than equal to 0, it's greater than 0. Sorry, if it's equal to 0, we're okay. Yeah, you'll see that, by the way. If we take a look at this quadratic formula here, this part, it's exactly what it says, right? D plus 2p quantity squared minus 8 SD. It's here, we'll take this. Watch, we do this less than 0. You get the same formula. You get D plus 2p squared over 8. Right, add 8 ds over here, 8d. And that gives you exactly what we got here. It's just kind of neat. Quadratic formulas are kind of, quadratic functions are kind of fun for this reason. So anyway, yeah, so that's the determinant, I think it's the determinant of the quadratic function. We want to, so I could have calculated that a lot faster. For whatever reason, I didn't think about it. What we want to do is say, so if this exists, if it doesn't exist, then we can use the other form. We can assume that you just take as much as you can from the function. This means that S is very large, basically. I don't fully understand that either, right? This function doesn't ever hit 0. That means that, what does that mean? Oh, I know why. Because the term, yeah, okay, this is why. Because the term that you're increasing, the term that you're adding, then subtracting from, right, that's why. Because you're subtracting a number that's decreasing. So eventually you're going to actually increase your wealth. That's why this is so confusing. Because if the price is what you're paying keeps decreasing below 0, then it's you're paying a negative price, means you're gaining wealth by engaging in the transaction. And so as part of the problem, they said, okay, we're going to stop gaining, you're not going to ever gain wealth, stop at a certain cutoff point. But in theory, you would actually keep going. So actually, what you'd end up doing is, yeah, that's probably why my calculations were way off. It's because I wasn't really thinking about it properly. So you would actually want to get the maximum in that case. Just get the maximum benefit before the cutoff point, which is just k every time, which we defined over here. So you would switch to k equals this thing in this case, and then otherwise, then you can use the quadratic formula to figure out how far you can go before you are in debt. Yeah. How does that work? Let me think about that too. Oh, I think your non-coding videos are interesting. In the groove, for instance. Gonna go see a friend. Have a nice day. See you. Oh, I'm sorry, Prince Poke. I didn't realize you're gonna go. Thank you. I appreciate that. I think, yeah. I'm okay. I'll probably do the more non-coding videos too then. And thank you for the heads up, the feedback. And I apologize I didn't read your comment for 10 minutes because I'm freaking so engrossed over here. Yeah, I guess okay. So I'll do the non-coding videos more, I suppose. Then, yeah, I have a whole list of stuff that I can do, videos, a lot of ideas, and then I like the groove. Yeah, the groove is nice. Definitely like the groove. It's very nice. I have to do that more. Definitely. Today is a good day for that. Would be a good day. What else am I missing? But yeah, thank you for popping in. Probably may not still be here, but thank you for coming by. So what else I've got going on here is so if it's the case that we're dealing with imaginary numbers, then we're going to want to just default to the maximum benefit possible, the cutoff point. Just go right to the cutoff point. If it's not, if it's not imaginary though, then that implies that we will hit a certain point. We want to use probably the largest alpha, I think. Yeah. So okay. So we can do if d plus 2p squared over 8d is greater than s, or rather s is, hold on, get this right, s is greater than this, use s is less than or equal to, then let q equal this thing. And we know that q is greater than 0, implies square root of q is greater than 0, which implies that d plus 2p plus square root of q over 2d is greater than d plus 2p minus square root of q over 2d. And we select alpha equals d plus 2p plus square root of q over 2d. Right. Then and use as before. Alright, so we do the same thing that we did last time, except this time around we use a different value for alpha p, alpha prime. So it depends on what we get for this, if this q is greater than or equal to 0, less than or equal to 0. So let's do it that way then. Let's do it that way. Let's say Q is going to be this thing, which is D plus 2P, D plus 2P squared. So 2, is that P? 2P plus D squared times itself. I don't think there's a squared function in Clojure. Minus 4d2s or 8ds minus 8ds. Okay, that's Q. So we say if Q is greater than or equal to 0, then we'll take this other function, which is, we'll do this one. Otherwise we'll take floor of the difference of Km. That's alpha prime, which is, I don't know if this is the correct thing either. I'm thinking about it. Oh, got it. That's why. If Q is less than 0, then you're not going to use the quadratic formula. You're going to use this thing, which is right, sort of the total cost of using K, and then divide that by M and add that. Take the floor of that and add that to what K is. Right, which this could be 0. And you just get K. And finally, right, so this is, we're going to get this alpha prime, which is D plus 2P plus square root of Q over 2D. Not this value at all, no. D plus 2P, so add 3 things, D, 2P, square root of Q, of Q, which is defined below or above, and over 2D. Right. Now the interesting part, so alpha prime, right? So we can do the same thing we did here. F prime S minus F of alpha. I think this is correct now. Let's see how this goes. 9. It's supposed to give us 0. No, man. No. No. What are you talking about? No. No. Maybe it's supposed to be the last one we want. We want F to be, no, we want F to be as small as possible while still being positive. Well, we're crossing over the 0, so I think we actually want not the first but the last in this instance. But this is pretty, this is not going to work either way. Also, hello? Is this thing on? Did I break it? What happened? Come on, man. Nine and 10. What is going on, man? What is going on? I guess the servers are having some issues. Oh no. Oh no. Oh. Problem is this anyway? I think the server's having some issues. Could also be my connection. No, I don't think so. I've been doing this for 2 hours now. Holy guacamole. Jeez. Uh-oh. Uh-oh. Well, this isn't great. This isn't great. Okay, Hello World is okay. So it's just HackerRank is having some issues. There's a Reddit we can look at. Twitter. Oh man. This guy's a very Indian company. That's what it is, I guess. Where is tweets? Sign up for Twitter. I don't want to sign up for Twitter, man. Just want to know if it's just me. Everything's working for us. What is happening here? Loading the page. I don't know, man. I don't know what's going on. Oh, it's loading. It's going slowly. Alright, let's go back to the calculations here. So this should just fail. We were getting 9 or 10. Should be 1. Should just be a 1. 100 minus 180 minus. Now why are my calculations off though? What the heck is going on? If it's 0, right? So I think the issue is, so what's Q? That's D plus 2P squared minus 8DS. S is 100. D is 19. P is 20, or excuse me, P is 100. What are these things? Oh, I don't even know. I should probably just label this. Oh, come on, man. error connection reset. What is going on? Hello? Okay, there we go. Sheesh. Alright. Looking for Halloween sale. I guess I took the problem down, I don't know. Okay. So what we're looking for is what's the input look like? It's P, D, M, and S. Okay, P, D, M, and S. P, D, M, and S. All right. So this 100 is not as P. S is 180, I think. P, D, M is 1. And S is 180. All right. So what's wrong? Q is 19 plus 2 times 100 squared minus 8 times 19 times 180. I get the feeling this is negative, and that's why we're having issues. Eight times 19 times 180. No, this is positive. Okay, so that's all well and good. That means we have square root of that, 20,601. Square root, right? It's about 143.5. All right, and now we're gonna say D plus 2P plus that. D plus 2P plus square root of Q over 2D gives us approximately, so D is 19, P is 100, this is about 143.5, and we want to go over, where's D? 19, okay. Which this is about 19 plus 200 plus 143 divided by 38. It's about 9.5. Yeah, about 9.5. All right. What? Excuse me? This is not... This is not 0, I think. I think this is maybe part of the problem here. I think the issue is pretty simple, and that is that this curve hits 0 twice, and we're picking the larger. We should actually be picking the smaller one, I think. Right. Is that right? Because the larger one may be way past the cutoff point. In fact, there's 2 cutoff points. One of these is alpha's got to be positive, and alpha's got to be less than the cutoff point. So there's two positions. Oh, I see. You're actually trying to get the largest. This is so confusing. This is so confusing. I don't know, man. This is crazy. Come on, man. Oh my goodness. Oh. Excuse me. Excuse me. The reason why you're never going to pick the second one is because this is a negative value and then this is a positive value. Which means that what we ended up doing is we decreased our wealth, or we decreased how much we have to pay until it's actually negative how much. Yeah, we decreased the price until it's negative, which, yeah. So what this means, if we're over here, is it means that we decremented the price from how much we have until we were in debt, and then the price that we were paying decreased so much that it became a negative number that we're paying, which now increased how much our total wealth until we're now out of debt. That's what we did on this curve following this. So we actually spent all our money, went into debt, and then the price went down, so then we paid back the money and went out of debt. That's why we can't use the second part of the curve, because it don't work like that. It don't work like that. Oh, it's really funny, man. It don't work like that. No, it don't. So really, we do want this one, actually. Holy smokes. How do you get a machine to figure all this out? You know, if you're going to write a piece of software that can write code like this, I don't think so. It's too much stuff to think about. That's so hard. That's hard. Alright, that's hard. It's really funny, but it's hard. It's probably doable. It's just really challenging. It's a lot of challenges, I guess. So we actually want this one every time. This one. That's the one we want, which is going to be 0, 1, I think, in this instance. So now the thing is, though, is this really the case? Is this really the only time where you use a definitive? So okay, all right, I got the idea. If it's the case that we never hit 0 on this curve, right? Then we don't actually care about this bound ever. Don't care about it. And we're going to use this one right here. This is exactly where the price cutoff is. It actually should be, in theory, somewhere down here. As you're going down, it'll be like here. Right? Because after this point, the price is, you're starting to make money. So you'll never take this second alpha. But if this is imaginary, then you're going to take this alpha. But what if it like just hits here? Well, the thing is, it's kind of a problem, huh? If you hit this alpha, or even if you just hit, like what if you go past this point and you still hit 0? Yeah, that's what I'm missing. Something like this, like much wider kind of a thing, something like that. No, I'm wrong. I'm wrong. This logic doesn't work, man. No. It's, oh. There are a few different things to consider, huh? If you think about it more, you'll eventually come to a more concise, simpler answer. But this is too funny. It's like, oh gosh. All right. See, this causes problems too. This second curve, and the reason is it does hit 0, but this point is way beyond the breaking point. That's the issue, right? So really, what you need to do, as it turns out, is if okay, if the curve is not imaginary, right? If the root is not imaginary, then what you're going to want to do is consider where the first root is, right? The first time you're going to start to go into debt. Find that point. I think I'm just wrong with it. I think I'm doing something wrong here. I'm just doing this wrong, I think. I'm thinking about it. Yes. No. Yes. Okay. I think I got it. So basically, you've got a whole boatload of different curves. The only time where you're actually going to consider the parabola is when you go into debt before this point. That's the only time you care about this parabola. That's when you get your alpha. And I think you take the floor every time, because you take the roof, then you're going too far. That's it. That's what we're missing. And that's a simple check. You don't actually need to care about whether or not this is imaginary. It doesn't matter, because if it's imaginary, you're definitely not going to hit this root. But this condition that you hit here, like that, this is positive, this difference. At this point, you're still positive, no matter what on the curve. That has nothing to do with whether or not it's imaginary. That is the diff. Okay, so I think I understand now. Holy smokes! Talk about like challenging here. So all right, we don't want to do Q. We want to do diff K. If diff K, we're going to return this guy, right? That we suppose that we halt before we go too far down the curve. Otherwise, we are going to use the first, and actually it's not even the first. It's not even, there's no sort by here. It's literally just it's actually just Q, not Q. This calculation. It's the floor of alpha prime, not even floor of alpha prime. Here we'll choose alpha equals the floor of d plus 2p minus the square root of q over 2d. Holy guacamole. Okay. Yeah, that's what we're gonna do. So d plus 2p minus square root of q. So q stays the same. And I don't think we need this alpha prime anywhere either. Not necessary. Don't even need f prime anymore. Don't need any of these. Oh, f prime is diff k, so I guess you do need f prime. F k, you have q, diff k. We're gonna say just alpha. It's gonna be no. We're just gonna inline this here. So this is the square root of q. So math square root of q, right, minus d plus 2 times p. So 2 times p plus d minus the square root of q divided by 2 times d. And then we've got, it's going to take the floor and make an int out of that. And that's it. All right. Talk about involved. Talk about missing stuff, though. Sheesh. Sheesh. All right, let's try some of these now. Unbelievable. Unbelievable. So 199, all right, so 0. What's the other one? That's what we expect. How about this? This should be a 1. This was an interesting question. I like this. Really, really got me. Didn't really exercise too much of the, well, I guess a little bit of Clojure. Not too much Clojure, more of the maths side of things. Sort of thinking about logic again, which I don't always do. How to solve problems like these. I think you just get 1 for this, right? Yeah. Okay. All right. See how we do. See how we do. Oh. Okay. Hey, okay. So there you go, that's constant time solution. Oh my goodness, man. That was so much more involved than it needed to be. But yeah, that's how you can do that in constant time. Very close to a closed form solution. Really very close. Very, very close. But yeah, the logical part, the part that I was really missing is that you basically have like a cutoff. You have a parabola and you've got 2 cutoff points, right? You can't use alpha that's less than 0, and you can't use alpha beyond this is alpha equals k, right? And then you've got a few different variations of curves. So you can have a curve that looks like this for this is sort of your money as you're buying things. It could look like that. It could look like this. I don't know. Could look like this. And it could look like this. And the differences between these, there's like some pretty key differences here. So if you hit this cutoff point, no matter what the reason, then you switch to the other curve, which is just a line downwards. But if you're in this range, you're this kind of curve where you're gonna go into debt before you hit this cutoff point. That's when you've got to employ the quadratic formula to figure out what is this first root, and that's the alpha. You're gonna pick the alpha just before that point for how many steps you're gonna go, and that's your total number of steps. Like obviously you're gonna go into debt beyond that, so you're not going to be you're never going to reach this point over here, right? You're nowhere close to it, and you can't add. Right. That's actually the point. So this happens before this point. Now, if this point, if you check this point and it's non-zero, this difference point, meaning there's some, meaning you can actually reach here, and then you're going to switch to the next line. Well, then you have to operate as if you did reach here, and then you go from there. That's a simple calculation as well. It's because it's linear after that point, so it's a very simple calculation. So if you can reach here, you suppose that you do every time, no matter what the curve looks like. If you can't reach here, that means that you went under well before, and then you pick the point before you go under. So the logic is kind of simple, but I got kind of caught up in the weeds. That's how you can do this in constant time. Cool. I will cut this video up, or cut this stream up into a video, and so I'll end stream now. Thank you guys for watching. That was the 5th problem. I think we got 5 more to go. I think we'll do a couple more easy ones. Like I said, we're still kind of getting comfortable. Do a few more problems, and let's put this in. I'm gonna go end stream, use the bathroom, come back, cut this video up, I'll put it up as like a sort of a condensed version, and then we'll continue the next problems. So thank you for watching. Take care.